So continuing on with our Lorentz transformation, now we're going to look and see what happens to the other absolute that Newton talked about, which was the length of an object. So just to remind you, here was our Lorentz transformation, here was pictorially, and the only thing that's new from last time, we said that the time, as long as one of them is at the proper time, doesn't matter who's at the proper time, the other time is always going to be a little bit bigger. So we said moving clocks run slow. And we said if you go at 86% the speed of light, that gamma, that factor right there became 2. So that if two rocket ships were moving by each other at 86% the speed of light relative to each other, they each would see their own clocks running normally. They'd each see each other's clock running twice as slow. So they couldn't tell who's moving. They have to see symmetric things. So now let's look at length. We said length was the other absolute from Newton. And so if we look at this, let's say from Mary's point of view, let's say there's a stick. So we have, here's Mary's point of view. We have some stick right here. Some stick. Has some length L. Right there. Now how do you get the length? Well, what do you have to do? You have to measure this position and you have to measure this position right there. So you have to measure the right, that little R means the right side of the stick, and you measure the left side of the stick, and you subtract those two X values. So L is going to just be X sub R minus X sub L. Now, this stick, for Mo standing here, maybe Mo's the one carrying it right there. There's Mo. I guess I should make him in red right here. So here's Mo. He's carrying the stick. To him, this stick is not moving. This stick is at rest to him. So we're going to call this the proper length. So we're going to put a little circle there. This stick can only be at rest can't be at rest relative to both Mo and Fred. So this is proper length. Proper length. Which means what? It means that the object is not moving relative to you. The object is at rest. Object is at rest. Relative to you. Well, that's what I mean by at rest, relative to you. Okay. Now, these should be also in red, X sub R, because that's what X sub R, and they should be primes, because Mary's doing it all, so these should all be in primes. Because I want to know how long is this stick going to be now to Fred and Frank and all of those. So that means we get an X sub R without the prime, and we get an X sub L without the prime. And we can say that Fred and Frank and Francis, they're all going to measure the length of this stick as X sub R minus X sub L. But to them, this stick is moving. It's moving off to the right. Now, the only thing is, if you're going to measure the length of a stick, and you're going to measure this position and that position, and this stick is going by, you can't measure this position now and that position 3 seconds later, because you measure this position and then now you measure that. You're going to get a distance way too big. You have to measure these 2 points at least at the same time. So must measure at the same time. Measure at the same time. Now Mo, he can measure this position and this position anytime he wants. He could measure this today and that tomorrow. It's not moving, so it doesn't matter to him. So on this right here, Frank, these two have to be measured at the same time in Fred's frame, and if it's at the same time, these two events have got to be almost like this and this. It's not the same time in Fred's frame. His time is going like this. Okay, so now we've got these two right there. We got this one and we got this one. We want to know, so what we're going to do is we're going to say L naught prime, this L naught prime is equal to, remember, since these are at the same time, that means t at the right equals t at the left. Not for this one. Mo can do it anytime he wants. Okay, so if we just plug in, we got x sub r prime minus x sub l prime. X sub r prime minus x sub l prime. Now we'll just plug in. We'll go from the prime to the n prime. So we'll just plug in right here. There's our prime, and we want to go to unprime. So this becomes x sub r minus v tr all over the square root of 1 minus v squared over c squared minus x sub l prime, which is x sub l minus v TL all over the square root of 1 minus v squared over c squared. Now we said that TR and TL are both the same. Since they're both the same here, both of these two terms cancel out. This one's minus, that one's plus. So these two cancel out. And we get L naught prime is equal to x sub r minus x sub l is L divided by the square root of 1 minus v squared over c squared. We don't want to know what Mary sees, we want to know what Frank sees, so we want to solve for L. L then is equal to L naught times the square root of 1 minus v squared over c squared. Well, since 1 over 1 minus v squared is bigger than 1, when this is in the numerator, it's less than 1. So this number right here is less than 1. So that must mean that L is less than L naught. L is less than L naught, which means that, remember, this L naught prime, sorry, that's L prime right there. This is the length that Mo saw. The length that Fred sees is less. So Fred sees this shortened right here. So moving lengths shorten. Moving in this direction right here. Moving, well, I should just say moving lengths. Lengths shorten. And we know that if you go at 86% the speed of light, instead of this being 2, it's the reciprocal, so it's a half. So at 86% the speed of light, the length of this stick, this L, would just be 1/2 L naught. So if I ran by here at 86% the speed of light, carrying this stick, you would only see it that long, 1/2 meter right there. Okay, well, what if we turn it around? What if Frank is the one with the stick and Mary goes by or Mo goes by? So here we've got the stick right here, and now we've got Fred right here holding the stick. So now this is Fred holding the stick, and he measures an x sub r, and he measures an x sub l, and he measures that length to be x sub r minus x sub l. Now this length isn't moving relative to Fred, So this is the proper length. It's at rest relative to him. Mary, or Mo, on the other hand, is going to measure an x sub r prime and an x sub l prime, because this thing is actually relative to Mary. This thing's heading off that way right there. And so they'll measure L prime, which is x sub r prime minus x sub l prime. Again, Fred has the proper length. Okay, so now we just want to know how long does Fred see it right here. Well, let's just do it exactly the way we did right here. We said L. Oh, also, Mary, since this stick is moving, Mary has to measure these 2 points at the same time. You can't measure something moving, the length of it, if it's moving on you. So that must mean that TL prime and TR prime have to equal. TL prime has to equal TR prime. So we can say L naught is equal to, right here, x sub r minus x sub l. So it looks like we're just going to plug in what? This equation right here. We're going to go from the unprime to the prime. So that's going to be, so we're plugging into this one right here. So we got x sub r prime plus VTR prime all over the square root of 1 minus v squared over c squared minus x sub l prime plus VTL prime over the square root of 1 minus v squared over c squared. But we said that these, again, these 2 times are the same. So we can get rid of that and that. And so we're left with L naught is equal to x sub r minus x sub r prime minus x sub l prime is L prime divided by the square root of 1 minus v squared over c squared, or L prime is equal to L naught times the square root of 1 minus v squared over c squared. So it looks like L prime is less than L naught. Over here, L was less than L naught, I guess it's L naught prime. It looks like who's ever holding the stick is the longer one. If it's moving with respect to you, either way, it's going to be shortened. So let's just say we have 2 people and 2 rocket ships passing by each other. This guy has a meter stick and this guy has a meter stick as they go by. This guy's going to see his own meter stick to be 1 meter. If they're moving at 86% the speed of light, he'd see this one moving by at a half a meter. If you're on this one, you'd say mine is 1 meter, but yours is a half a meter. They each see each other's stick half as long as their own. So if they compared sticks when they went by each other, they're not going to agree. This guy's going to say, no, mine's a meter, yours is a half a meter. You're going to say, no, mine's a meter and yours is a half a meter. They each see symmetric. They can't tell who's moving. Okay, so you get that symmetry right there. And for this, remember, we said Mary had to measure it at the same time. So over here, we would have had to pick 2 points that were at the same time in Mary's frame, so maybe like this and like this right there. And so they would have been 2 times were the same. Okay, so now that once we have this, we can go back to our Michelson-Morley experiment and explain why he didn't get his results weren't that good. Why he couldn't find anything. Well, remember, we had this place where the light went up and back down, and we had over here, this light went back and forth. And we said that the time it took to go, we said the drift was going this way, the drift of the ether drift was going this way. And we said this was A and D, and this was C. And we said the time it took to go from here up and back down again. If you look back at the notes, this was A to D to A. This was 2L all over C, 1 over the square root of 1 minus V squared over C squared. And the time to go back and forth this way, time A, C, A, was 2L all over C. It didn't have the square root. It was just 1 over 1 minus V squared over C squared. Well, let's just say there's no drift. If there's no drift, then both V's are 0 and you get the same thing. But now let's just say this thing is moving right here. If this object is moving, this length doesn't get shortened up, but this length does get shortened up. Instead of being instead of being this one, instead of being an L from here to here, it becomes L times the square root of 1 minus V squared over C squared, because that's, remember, we said the lengths become, you just multiply it by this term. So if I replace this L with this one, put that in there, all it does is add an extra square root right here, 1 minus V squared over C squared, and you notice the square root over this gives me the same thing. So no matter how fast this goes, you could think of it as, oh, the length is just decreasing. It's fooling you to keep this time and this time the same. Okay, so this is the reason why, Michelson could have never found the movement here. Well, we already said that this gamma factor was this right here. If you go 86% the speed of light, this becomes a half. So let's say we look at something. Suppose we got a snake here. A snake. My snake's going to look like a stick, but it's a snake. And let's just say its length is 2 meters. That's how long he says he is right here. He says, I'm 2 meters long. And let's say he moves this way. He's a fast snake. He can slither along at 86% the speed of light. Well, if he can slither along at that speed, we know that this gamma factor is a half, or this 1 over gamma is a half. So we would see this thing as only, for us looking at it, we would see you're only 1 meter long. We would see you shrunk down to 1 meter. Now let's say you have some knives here. You have a knife, 2 blades. Here's 2 knife blades. They both come down and they're 1 meter apart from each other. And so this snake, if he goes by at 86% the speed of light, these knives should go down and miss him completely right there. And so he feels safe. But that's from our point of view. What about from the snake's point of view? From the snake's point of view, he would say, I'm 2 meters long. I'm not 1 meter, I'm 2 meters long. And then how far apart do I see those 2 knives? Well, those 2 knives are moving this way relative to the snake, and moving things shrink, and so they're going to be shrunk to a half a meter. So now the knives are only a half a meter apart. And he says, I'm not going to survive this. There's no way. These 2 blades are going to come down and get me right there. But us looking at it, we say, no, it missed you right here. What happens? Does he die or does he survive this right here? I should say we can take a picture of it right here. We got a camera out here. We can take a picture of it and we actually can say he survives. Now we have to figure out why doesn't he think he survives right here. We'll worry about that a little bit later right here, but we would figure it all out if we drew it on one of those Minkowski diagrams right here, but I don't want to do it right now because it'll be similar to one of your homework problems in the second segment right here. You'll notice that this allows space travel, this length contraction. Because let's say here's Earth right here. And let's say the furthest object you can see with the naked eye is actually the Andromeda Galaxy. It's outside of our galaxy. Here's the Andromeda Galaxy out there. The length, the distance from there to there is 2 million light years. Light years. So it takes 2 million years just for light to get there. Can you get there in your lifetime in a rocket ship going less than the speed of light? And the answer is yes, you can. Why? Well, actually, I should say it takes light no time to get there, but when they say in our frame, it takes like 2 million years. Well, the reason why it doesn't is because as soon as you get in a rocket ship, once you get up to 86% the speed of light, this distance is not 2 million light years. It's only 1 million light years. Now it's only a 1 million light years. Let's say you get up to 99% the speed of light. Then this length is even going to contract more right here, just from this equation. And we could just say, well, how fast do I have to go to contract it by, say, 2 million times? So you might have to go like 99.9999 or something. You could contract this distance so that that galaxy is only 1 light year away. And if you're going at this speed and you're only going 1 light year, it's like a one year there. And if you don't like it and you turn around and you come back, it's another year back. You made it there and back in 2 years. The only thing is, when you get back, you go, where'd everyone go? Because when you get back, it's actually going to be 4 million years in the future, right? So you can move into the future if you want to. Really, well, we're always moving into the future, but you can move into the future at a different rate if you want to. You can't go back if you don't like it. So, but we'll come back to that again later. But it is possible. Just shrink up the distance. So I wanted to do one last problem on the transparencies, another one of these, just to get some more practice on it. So now let's look at another problem. This is on the Enterprise and the Klingon battle cruiser. It says, a Klingon battle cruiser is equipped with a disruptor cannon mounted at its rear end, which can only fire perpendicular to its direction of motion. So if it's right there, it fires perpendicular to its direction of motion. So there's the Klingon battle cruiser, there's the Enterprise. The standard Klingon tactic is to fly by its enemy and fire this cannon as the front end of the battle cruiser passes the enemy's ship's rear end. So right here, you see when the front end of the ship passes the rear end, it fires and gets them. In the following discussions, assume that the battle cruiser flies by so closely that you can neglect the time it takes for the disruptor beam to travel from the cannon to the target. He goes right by it. The Starship Enterprise, which is the same length, they're both the same length right here, when they're both at rest, is about to be attacked. Just to show you, this is the Enterprise's frame, so he's like Frank's frame. And the Klingon, there's his X prime, and there's his CT prime frame. And so Dr. McCoy is worried that due to Lorentz contraction, the Klingon battlecruiser will be shorter than the Enterprise and therefore cannot miss. So there's his theory, is that the battlecruiser will shrink due to length contraction and get him. Captain Kirk, on the other hand, claims that the Enterprise will be shorter than the battlecruiser when seen in the Klingon's frame, so there's nothing to worry about. So Kirk says it's them that's doing the shooting, so it's their frame of reference that matters. And McCoy says, damn it, Jim, we're the ones getting shot at. It's our frame of reference that matters. You, Mr. Spock, must calmly draw a space-time diagram and explain to them which one of them is right. And McCoy says, Spock, are you out of your Vulcan mind? We're about to die and you find nothing better than to draw pictures? And Spock says, Doctor, I assure you that I'm doing the best I can under the circumstance. So we need to answer, first of all, at which space-time point labeled A, we got A, B, C, D, E, F, G, and H, does the front end of the battle cruiser pass the rear end of the Enterprise? Well, here's the front end of the battle cruiser. Where does he pass the rear end of the Enterprise? That would be right there at C. As the front end of the battle cruiser passes the rear end of the Enterprise, right here, at which space-time point is the rear end of the battle cruiser in the Enterprise's frame? Well, here's the rear end. When the front end is here in the Enterprise's frame, these are equal times. So it'd have to be the intersection of these horizontal lines and this line, which looks like B right there. That's what B would be. As the front end of the battle cruiser passes the rear end of the Enterprise, again right here, at which point is the space-time point in the battle cruiser's frame? Well, these are the same times. So the rear end, it would be the intersection of this line and this, because these are equal times, so it would be out here at E. Out here at, as the front end of the battle cruiser passes the rear end, at which point is the front end of the Enterprise? The front end of the Enterprise is right here, and it would be equal with that line, so it's actually F right there. There's the front end of it. At which space-time point does the cannon disruptor fire? Well, he just fires when at this point, but on the Klingon ship, that would be right there. There's the end of the ship. There's the back end of the ship right there. When the disruptor cannon fires, where is the front end of the battle cruiser in the Enterprise's frame? In the Enterprise, the front end in the Enterprise frame, if the back end is right there, the front end is right there. So when he fires, the front end of the Klingon ship is just right there. There's the back end. It misses him. Just like, so Captain Kirk's theory is correct right here. Remember, he's going to fire, it's the Klingon that's firing, and the front end of the Klingon ship is right there. The back end of the ship is way over there. So, as usual, Captain Kirk wins this argument. So again, we can make a lot of easy answers just with little pictures rather than going through all the equations right there. Okay.